This is your presenter Asloob Mudassar, and I am presenting slide number 12C of the course on atomic and molecular physics. Today I shall be covering the following topics: fine structure, spin orbit coupling, fine structure of one electron states, explanation of doublets. This lecture is in continuation of the previous two lectures covered in slide number 12A and 12B. So it is desired that you go through those two lectures first, and then you can easily understand this lecture. In the lecture number 12A, the following important points were discussed. That is, the relationship, that is the orbital angular momentum, the orbital magnetic moment. These two quantities were discussed, and their relationship as given in equation number 13 was also discussed. And other relationship in equation number 16 was discussed. In magnitude form, the orbital and magnetic moment is related with the magnitude of the orbital angular momentum was discussed and presented in equation number 12. Then you know that the z component of the magnetic moment was discussed, and this orbital angular momentum magnitude of the orbital magnitude of the orbital angular momentum was represented in terms of the orbital magnetic moment, magnetic quantum number, which is ml. So ml is actually the orbital magnetic quantum number, and the relationship is given over here. Then you see that the maximum value of this component, that is the maximum value of the z component of the orbital magnetic moment, was related with the quantum number L. So on the right hand side in equation number 18, you can see that L stands for the quantum number, orbital quantum number. Then in equation number 25, the magnitude of the orbital angular momentum was presented to be related with the orbital quantum number L. So you see that magnitude of the orbital angular momentum was equal to square root of L into L plus 1 into h bar, where L is the, where small l on the right hand side in equation number 25 is the orbital quantum number, whereas on the left hand side the quantity is the absolute value or the magnitude of the orbital angular momentum. Then you see that the z component of the orbital angular momentum is given as shown in equation number 24, which is equal to ml times h bar, where ml is the orbital magnetic quantum number. So orbital magnetic quantum number of the electron or the atom, and ml has a following possible values, that ml could be equal to 0, plus minus 1, plus minus 2, and so on up to plus minus l. That is the maximum value of the orbital quantum number is equal to either plus l or minus l. So you see that this was presented in lecture number 12A. Now in lecture number 12B, in lecture number 12A, we discussed the quantities which were related with the orbital thing. That is, we represented orbital angular momentum, we presented orbital magnetic moment, we presented a relationship between them, we presented the we expressed the magnitude of the orbital angular momentum in terms of the orbital quantum number. Then we presented the orbital magnetic quantum number. So these things were presented, and in slide number 12B, we presented the same things but for the spin quantities. So you see that equation number 29 here represents the magnitude of the spin angular momentum written on the left hand side, which is related to the spin quantum number s on the right hand side. So magnitude of the spin angular momentum s mod is equal to the square root of s into s plus 1, and outside that one we have h bar. Similarly, equation number 30 gives you the relationship between the spin magnetic moment and the spin angular momentum in terms of the parameter gs. Then you see that in equation number 31 we have the z component, which was represented as the spin magnetic moment. spin magnetic quantum number ms. So the ms has only two values. It is the spin magnetic quantum number, and the two possible values for the ms were equal to plus minus half. Then you know that the expression in equation number 32 gives you the relationship between the z component of the spin magnetic moment related with some quantities through the spin magnetic quantum number ms. So ms, you see that is the spin magnetic quantum number has only two values, ms is equal to plus minus 1. Then I presented there the orbital gyromagnetic ratio represented by gamma L, which was equal to GL times mu B Bohr magnetron divided by h bar. And then I also presented, as shown in equation number 38, the spin gyromagnetic ratio related with the parameters GS and Bohr magnetron divided by h bar. Then some experiments were presented there. For example, gyromagnetic ratio by Einstein de Haas experiment was presented. There we presented that mu s, that is the spin magnetic moment, and mu l, that is the orbital magnetic moment, are associated with the spin angular momentum s and with the orbital angular momentum of the electron respectively. Then another experiment was presented to confirm the directional quantization, and that experiment was given by the Stern and Gerlach experiment. In that experiment, mu, which is the magnetic moment, either that of the orbital magnetic moment or the spin magnetic moment, or actually the sum of these two magnetic moments, mu was presented, and this mu can be measured, and it has a directional quantization, that is its direction is quantized in space, especially in the presence of the applied magnetic field. So this was presented there in the Stern and Gerlach experiment. Then you see that it was also presented that in the presence of the external uniform magnetic field, all these four quantities, that is L, S, mu L, mu S, which are respectively the orbital angular momentum, spin angular momentum, orbital magnetic moment, spin magnetic moment, all these four quantities carry out precessional motion about the external magnetic field, and their experimentation and their precessional motion was presented in detail. So this was covered in lecture number 12B. Now I am going to present lecture number 12C. So I am going to present fine structure, and fine structure have a very strong relationship with the spin orbit coupling. Spin orbit coupling means that the quantities which are spin related will couple with the quantities which are orbit related. That is, mu s will interact with the mu l, and the coupling between the spin magnetic moment and the orbital magnetic moment is actually called, will give you further splitting, which is called fine structure splitting. So an overview of that one will be presented here. We have seen that all energy terms except terms corresponding to s electron are split into two substates. So except the s electron, what is special with the s electron? You know that for the s electron we have the orbital angular momentum equal to 0. When the orbital angular momentum is equal to 0, then of course the orbital magnetic moment will also be equal to 0. So the both quantities will be equal to 0, which when we have the s electron. S electron means that the valence electron is the s electron. And so except this s electron, all the other electrons, that is p electron, d electron, and f electron, for all these electrons there will be the spectral lines will be split into two lines, which we call as the two substates. This produces a doublet or a multiplet structure of the spectral lines. When only one electron, when we are talking about only the valence electron to be consisting of a p electron, d electron, or other f electron, for example, then in the case of a single electron we have doublet lines. That is, a single line will be split into two lines. And but in the case of, if we have more than two electrons, if we have more than one electron as the valence electron, then we have the structure which is called the multiplet structure. of the spectral lines. This is denoted by the generic name of fine structure. So fine structure is actually means that we want to see the details of the lines which are split into the doublets or the multiplets. So the splitting of those lines is called fine structure, represented in abbreviation by the Fs letters. So Fs, which is the fine structure, cannot be explained with Coulomb interaction between the nucleus and the electrons. Fine structure results from a magnetic interaction between mu L, which is the orbital magnetic moment, and mu S, which is the intrinsic moment or the spin magnetic moment of the electron, and this is known as the spin orbit coupling. So you see that if the two quantities, that is mu L and mu S, interact with each other, then such a coupling is called a spin orbit coupling. Depending whether the two moments are parallel or anti-parallel, the energy term is shifted somewhat. So you see that here mu L and mu S can interact in the configuration that both quantities are parallel to each other or both quantities are anti-parallel to each other. And in these two configurations, there will be a difference of energies between the two states, that is between the states when they are parallel and between the states when they are anti-parallel. And in these two cases, there will be a energy difference between the two quantities. Coupling of magnetic moments leads to an addition of two angular momenta to yield the total angular momentum. So you see that when there is an interaction between mu L and mu S, then you saw that in these vectorial form, they will combine together. That is a mu S and a mu L can combine together to produce another quantity which we shall see later, and such a quantity will be called as the total magnetic moment of the atom. And when their corresponding quantities, that is the L, which is the orbital angular momentum, and S, which is the spin angular momentum, when these two quantities will couple together, they will produce a quantity which we call as the total angular momentum, represented by the letter J. So corresponding to mu L and mu S, the quantity that we have will be called as mu J, and corresponding to the quantity L and S, the quantity that will be that is the resultant quantity will be called as J. So J will be called as the total angular momentum of the system, and mu J will be called, they will be regarded as the total magnetic moment of the atom. The following conclusions can be derived. L and S. L is the orbital angular momentum in vectorial form. S is the spin angular momentum in vectorial form. So L and S add to give a total angular momentum J of the atom. So in vectorial form, we can write that J is equal to L plus minus S. So this is the vectorial form. Even if you use only a single sign in the vectorial form, that will be enough to define the equation number 48. So J on the left hand side is the total angular momentum, and which is related with the vectorial addition of the orbital angular momentum and the spin angular momentum, as shown in equation number 48. In the magnitude form, you can take the magnitude of both sides of this equation and you can represent them as shown in equation number 49a. That is the magnitude of vector J is equal to the magnitude of L plus minus L S. That is the magnitude of the total angular momentum of the atom is equal to the magnitude of the vectorial addition of L plus minus L plus minus S. Now, so this is so in vectorial form, I have shown the total angular momentum in equation number 48, and in its magnitude form, the total angular momentum is shown in equation number 49a. Now you see that in terms of the quantum numbers, you see that when we talk about orbital quantities, we have orbital quantum number which is represented by small s, and when we talk about the spin quantities, we have the spin quantum number represented by the letter S. Similarly, we have a total quantum number J represented by J. So J is equal to mod of plus minus S. This equation, which is 49b, is in terms of the quantum numbers. So if you find out the total quantum number J of the atom, that will be equal to the sum of the magnitude of the orbital of the addition or the subtraction of the orbital and the spin quantum numbers. So this means that the minimum value will be the minimum value of J will be L minus S, and the maximum value of quantum number J will be equal to L plus S. So from the minimum value to the maximum value, from the minimum value L minus S to the maximum value L plus S, there will be some other values which can be obtained by the addition of integral by the integral addition. That is, L minus S is the first quantity, then L minus S plus 1, L minus S plus 2, L minus S plus 3. So keep on incrementing that one through the integer intervals, and then ultimately you will reach the final value, which is L plus S. So this is the meaning of equation number 49b. For a single electron, the value of the spin quantum number is S is equal to half. So remember, if you are talking about a single electron, then the value of the spin quantum number S is equal to half is a fixed value. And you know that in the present lecture and in the last two lectures, we are talking about only the case of the single valence electron. So here S is equal to half. What about if we have more than one electron? This case will be dealt later on. So S is equal to half is the spin quantum number for the case of a single electron. So for the case of single electron, you can write the previous equation as J is equal to mod of L plus minus half. Magnitude of the total angular momentum in terms of the total quantum number J is given by. You see that similarly, we have written a relationship similar to the relation given in equation number 50 for the case of the orbital things and for the case of the spin things. Similarly, for the case of the total angular momentum of the atom, we can write that the J mod, that is the magnitude of the total angular momentum of the total angular momentum is equal to the square root of J into J plus 1, and outside this one we have H bar. And you know that here in the square root we have J, which is the total angular moment, which is the total quantum number. So J is the total quantum number of the system, and on the left hand side we have the magnitude of J, which is actually the magnitude of the total angular momentum of the system. Now for S electron, we have L is equal to 0. So you can put the value of L is equal to 0 over here in the previous relationship over here. Then you have J is equal to 0 plus minus half mod is equal to 1 half. You know that only one value is possible. So it means that this is a singlet case. That is no doublet. That is only single value of J is obtained. So if you obtain a single value of J, you will say that it is a singlet case and not a doublet case. Then for the p electron, the value of the orbital quantum number L is equal to 1. So substitute L is equal to 1 over there. And if you carry out this mod, which is a mod of 1 plus minus half, you will get two values. When you add them, you have 3 half. When you subtract them, you have 1 half. So these are the two values over here. So it means that, so if you put the value of these two quantum numbers in equation number 50, you will get two values of the magnitude of the angular momenta, which is equal to square root of 15 divided by 2 into h bar, and then square root of 3 by 2 into h bar. So you see that here you are getting two values for the two values of J, two values of the quantum number J. So this is the case of doublet. So in case of S electron, we don't have a doublet, but in case of a P electron, we have the doublet values. Similarly, if you try the case of D electrons, for which the value of L will be equal to 2, you will find out only two values there. So that will again a doublet case. So for the single electrons, except for the S electrons, all the values of the total quantum number J will always be 2 in number. And of course, the magnitude of the total angular momentum will also have two values. and that will be the case of the doublet. So for the s electrons there is no doublet case, but for the p electrons we have the doublet case. Similarly for the d electron, for the f electron, and so on, we would have two values of j, that is we shall have the doublet cases. Like L and J, where L is the orbital angular momentum and J is the total angular momentum, the orbital angular momentum, with the J also has a directional quantization. That is, its direction is fixed when we apply the magnetic field. So it has a fixed value of J. And J's, and if the magnetic field is uniform, then like the orbital angular momentum L, the angular momentum vector J, that is the total angular momentum vector J, will also carry out a precessional motion about the magnetic field. And in that case it would have a Jz, which is the Z component of the angular momentum, will obey the following condition. And this condition is, you must be familiar of this condition, because such a condition has been written for the case of the orbital quantities and for the case of the spin quantities. For the orbital quantities this was written as Lz, and for the spin quantity this was written as Sz. Now for the case of the total angular momentum, the J component of the angular momentum in the direction, the projection of the projection of J, which is the total angular momentum of the atom, onto the Z component, or onto the magnetic field, will give you the Jz component, which is equal to mj times h bar, where mj is actually the magnetic, where mj is actually the total magnetic quantum number of the atom, and mj could have the following possible values. So mj is equal to 0, plus minus 1, plus minus 2, plus minus 3, and so on up to plus minus j. So if you account all these values from minus j to plus j, you will see that there are 2j plus 1 possible values of mj, starting from minus j to plus j with the integral increment. That is, the minimum value is minus j, the next value is minus j plus 1, the next value is minus j plus 2, and so on, until you reach the value of total value of capital plus j. So mj is the total magnetic quantum number of the atom. Note that L, which is the orbital angular momentum, and S, which is the spin angular momentum, J is the total or the resultant angular momentum of the atom. Now let me discuss the figure first. You see that I have applied external magnetic field B, which is the uniform magnetic field, to an atom. What will happen to an atom is that in case of you see that in the previous lectures, in the previous two lectures, we have discussed that the orbital angular momentum L in the presence of the external magnetic field will carry out the precessional motion about the magnetic field. And we have also discussed that in the presence of the external magnetic field, the spin angular momentum will also carry out the precessional motion about the magnetic field. There we discussed the pure orbital case and the pure spin case. But now we are going to discuss the cases in which these are not acting independently, but they could mutually interact with each other, because the spin magnetic moment mu s and the orbital magnetic moment mu l can interact with each other, and their corresponding quantities, that is the orbital angular momentum and the spin angular momentum, can also interact with each other to produce the total angular momentum j of the atom. And this is the case I am going to present. If you recall equation lecture number 12b, you will notice there that S is actually produced due to the rotation of the electron about its own axis, and L is produced when the electron revolves around the nucleus. So the direction of L is perpendicular to the current loop of the electron using a right hand rule, whereas S was perpendicular to the electron, was perpendicular to the rotation of the electron, where the electron rotate about its own axis, the direction of S will be perpendicular to that one. So we have discussed their individual directions. Now we are applying the magnetic field B, which you can see I have shown over here, the Z direction or the direction of the magnetic field. These two are taken for each other. That is, whenever you say that we are talking about the Z direction, it means that we are talking about the direction of the magnetic field. Or when you talk about the magnetic field B, it means that we are talking about the Z direction. This analogy is what we have accepted in the atomic physics course. So you see that when you apply the magnetic field, external uniform magnetic field, what will happen? You will notice over here the green loop. You see that there is a green loop over here, which is at the tip of the vector J, which is the total angular momentum vector J, total angular momentum vector J, and you know that it has a tip. When the vector J precesses its motion, carry out its precessional motion about the magnetic field V, like this one, then of course a loop is traced out, a cone is formed due to the precessional motion of the total angular momentum J of the atom about the magnetic field. And then you know that J will have three components, Jx, Jy, and Jz. The Jx and Jy component will be averaged to zero due to its precessional motion about the magnetic field B, whereas only one component which we can measure is the Jz component. So Jz component will survive, and it is the projection of the vector J onto the axis, onto the Z axis, or onto the magnetic field B. So you see that the tip of the vector J will carry out a precessional motion, and it will and this loop is formed, which is shown in color green, and Jz is the Z component of a vector J. Now what about the other quantities, orbital angular momentum and the spin magnetic moment? We have discussed their precessional motion as a pure orbital case and a pure spin cases in the previous two lectures. Now you see that here this is the case when they are coupled. So S and L add together. For example, you can see that I have shown the orbital angular momentum L in red color, and the precessional motion, it carries out a precessional motion not about the magnetic field, but it will carry out its precessional motion about the vector J. And you will see that it traces out a red loop with its tip, with the arrow tip of the vector L. Due to the precessional motion, a loop is traced out about the total angular momentum J of the atom. Now you see that the vector S has been added over here at the tip of the vector L. And you know that L and S of course would add vectorially to give you the total vector J. Because below that one you will see that S has been shown as an independent quantity, that the spin angular momentum will carry out its precessional motion about the vector J. And a loop shown in blue color is traced out by the tip of the arrow of the spin angular momentum. So in the presence of the magnetic external uniform magnetic field B, and in the presence of the spin orbit coupling. And you know that when I talk about a spin orbit coupling, it means that the interaction of the quantity mu s and the quantity mu l will be interacting with each other. That is, the spin magnetic moment and the orbital magnetic moment will interact with each other, and of course their corresponding angular momenta will also interact with each other. That is, the orbital angular momentum L and the spin angular momentum L will interact with each other to form the total angular momentum J of the atom. So then J will carry out its precessional motion about the magnetic field, L will carry out its precessional motion about J, and similarly S will carry out its precessional motion about J. So in the presence of Ls coupling and in the presence of the magnetic field B, L and S both will precess independently about the magnetic field G, about the angular momentum J, and the total angular momentum J will then precess about the magnetic field B. You know that if you want to add two vectors, you can move one vector anywhere towards the other second vector, provided you don't change the direction of the vector and you don't change the magnitude of the vector. So the vector L, you know that was centered at the current loop of the electron, whereas S was centered at the rotation of the electron. So we can move vector S and vector L in such a way that we can you see that combine their initial values where they start, where they originate, or where their tails form. So I have joined vector S and vector L at their tails with keeping their magnitudes and their directions fixed. So you see that they are they will precess about the vector J, and then I have moved this vector S at the top of the vector L to make them as a to make them head to join combination, and then you see that L and S will add to give you the total value of J. So now let me briefly say that when you have pure L and S cases, independent of there is no coupling between there is no ls coupling, then you see that when you apply the magnetic field, L will precess about the magnetic field, S will also precess about the magnetic field. But when there is an interaction between them, which we call spin orbit interaction, then you see that S and L will interact with each other to form you the total angular momentum J of the atom, and in that case J will precess about the external uniform magnetic field B, L will precess about the total angular momentum J, and S will also precess about the total angular momentum J. You know that we have other quantities mu L and mu S, which are actually directed opposite to the direction to the vector L and S respectively. Let me show you these two quantities first. For example, look over here. For example, in equation number equation number 13 and equation number 16, which are the vectorial representation, which are the vectorial relationship between the orbital angular momentum mu, orbital magnetic moment mu L, and the orbital angular momentum L. You see that there is a negative sign over here. It means that mu L is directed opposite to the angular momentum vector L. Similarly, in case of the spin, you can also see equation number 30 that there is a negative sign between the two vector quantities S and mu S. So it means that mu S, which is the spin magnetic moment of the electron, will be directed opposite to the spin angular momentum of the electron due to this negative sign. And you see that I have not shown magnetic moments, that is, I have not shown the spin magnetic moment and the orbital magnetic moment in this diagram. So if you show the mu L, which is directed opposite to L, and if you show mu S, which is directed opposite to S, and then you see that mu S and mu L and mu S can be seen in opposite direction to vector L, and they will also precess, but they will precess about the minus B direction. And of course minus J vector will then be formed over there, and then of course mu J, which is the resultant magnetic moment of the atom, will also be formed over there, which is also in opposite direction to the total angular momentum J of the atom. So all the magnetic moment quantities, that is the spin magnetic moment, orbital magnetic moment, total magnetic moments, they are directed opposite to these S, L, and J quantities, as I have explained a little bit briefly a minute ago. Now let me read the paragraphs. In the presence of the applied magnetic field Vj precesses about z-axis or the B field. Both L and S precess about J. The opening angle of the cone of the precession is determined by the magnetic quantum number Mj. So you see that mj can determine the opening angle of the cone. We have discussed ms and ml previously, and if you see the previous two lectures, you will see that how we related ml and ms there with the opening cone of the with the opening angle of the cone. Now let's discuss for the p electron. We have L is equal to 1, S is always equal to half for the case of a single electron. So J, if you form the value of J will be equal to 3 half and 1 half. And if you have J is equal to 3 half is chosen for example, then Mj will be equal to 3 half, 1 half minus 1 half minus 3 half. So if you choose J is equal to 3 half, then the total magnetic quantum number of the system will be equal to 3 half, 1 half minus 1 half minus 3 half. Because you see that we have specified that the magnetic moment mj will change from 0 to plus minus j. So if j is for example 3 half, then of course then from 3 half to minus 3 half will be the possible values of j with the integer incremental separation. So j is equal to 3 half mean that mj will be from 3 half, then again 1 half, then minus 1 half, then minus 3 half. So at the extreme end, you will see that the values are plus minus 3 half. So you see that there are 4 possible values of mj. That is, if there is no magnetic field. That is, if there is no magnetic field, then you have the j is equal to 3 half will represent only one spectral line. But if you apply the magnetic field, then the j degeneracy is lifted. That is the level which was only a single level due to the value of j will be lifted into 4 values, will have 4 possible values of energies with mj value 3 half, 1 half minus 1 half minus 3 half. It means that the j degeneracy is lifted. J degeneracy lifted means that the value are now going to depend upon the total magnetic quantum number mj of the atom, and that is only in the presence of the magnetic field. And you know that the magnitude of the total angular momentum of the atom J mod will be equal to 3 by 2 into 3 by 2 into 5 by 2, the square root of these two quantities, and then multiplied by h bar, which is outside this square root sign. Because you know that in the square root sign we have j into j plus 1, and the value of j is 3 by 2 because we are choosing at the moment only a single value 3 by 2. And you know that okay, so in the presence of the magnetic field, the mj values you see that are shown from minus 3 by 2, minus half, plus 3 by 2, then plus half, then plus 3 by 2. And you know that the half values, plus minus half values have been shown with the green arrow, and the plus minus 3 half values have been shown with the red arrows. These have the total, the magnitude of these arrows is given by the magnitude of j mod j, the magnitude of the total angular momentum j mod. Their angular momentum, their magnitude is fixed. You see that all these 4 arrows have a fixed magnitude given by the j mod. And of course, the mj values have different angles, you know. So 4 different orientations are possible in the presence of the magnetic field. So it means that J, which was only shown to be a single arrow. You see that in this figure we have shown J to be a single arrow, carrying out precessional motion about the magnetic field. But in principle, it has 4 components. You see that these 4 components will carry out the precessional motion about the z direction or about the b direction. So precessional motion carry mean that each arrow with its tip will trace out a loop about the magnetic field B. So each arrow will trace out a loop about the magnetic field B, and their Z component along the B direction will be represented by JZ and will have the possible these values, that is plus 3 by 2 into H bar, plus half into H bar, then of course we have 0 in the center, then minus half H bar and minus 3 half H bar. These are the JZ values, and I have given a relationship for the JZ values in the previous case. So you see that you can notice that the value of Jz is equal to Mj times H bar. So if Mj has 4 values, then Jz will also have 4 values. And I have shown the projection of these 4 values onto the applied magnetic field B or the Z direction. So their Z components have been shown. So these are the Mj values, and there are 4 Mj values. So there are four arrows pointing for each Mj values, and these 4 arrows will carry out precessional motion about the magnetic field, tracing out their respective loops, and their Z component will be 3 half H bar, 1 half H bar, minus 1 half H bar, and minus 3 half H bar. Again, the Jx and Jy, these two components will be averaged out during this precessional motion. So a state with J is equal to 3 half is a four-fold degenerate. That is, the J value is split into 4 sub values, is a four-fold degenerate, and when the in the presence of the applied magnetic field. So in the presence of the applied magnetic field, the degeneracy is lifted, which means that the J is now going to depend upon further splitting through the Mj values. So due to the magnetic quantum number Mj. So this degeneracy lifting is due to the total magnetic quantum number Mj of the atom. So the simple case is that if there is no magnetic field, then of course only J will be present. But if you apply externally the magnetic field to the atom, then J will split into further. Then the vector J will split further into will split further due to the Mj values, due to the total magnetic quantum number of the atom. And then of course the degeneracy will be lifted. That is the energy of the level which was due to J level, was representing a single level due to the J value, will now be split into 4 levels, which we called four-fold degeneracy is lifted. Now the selection rules. So selection rules mean for optical transition. When we say that optical transition, it means that the transitions through which we have, that is the radiative transition, that is a wavelength emission occurs through such a transition, and such transitions are referred to as the optical transitions. So for the optical transition, the value that is the rule for delta J is that delta J should be equal to 0 plus minus 1. So the rule is 0 plus minus 1. But 0 to 0 transition is not allowed. So if you have J1 is equal to 0 and J2 is also equal to 0, then you see that their difference is equal to 0, but 0 to 0 is not allowed. So in this equation, which is delta J is equal to J1 minus J2 is equal to 0 plus minus 1, this transition is permitted except that both J1 and J2 are 0. So J1, one of them could be 0, but both cannot be 0. This is not allowed. So there is a magnetic moment mu G associated with the total angular momentum J, which will be discussed later. And of course, we can find out later that mu J will also be directed opposite to the angular momentum J, as we have seen for the case of the orbital magnetic moment and for the case of the spin magnetic moment in the previous 2 lectures. Now calculation of the spin orbit splitting. So you see that so far we have discussed that this is the case that we are considering, that is the spin magnetic moment mu s and the orbital magnetic moment mu l. Now they are in the position that they can interact with each other to form the total spin, to form the total magnetic moment mu j. And similarly, their orbital quantities, that is the spin angular momentum and the orbital angular momentum, can also interact with each other, and they form the total angular momentum J of the atom. So this is what the spin orbit splitting means. So you see that when they will interact, there will be a further splitting, which is referred to as the spin orbit splitting, or referred to as the fine structure. And we are now going to calculate how much energy is splitted. Can we do we are we able to calculate the splitting, that is the energy splitting, in through some mathematical relationship? This is what we are going to investigate. So calculation of spin orbit splitting in Bohr model. There is a small energy difference in the two orientations when L and S are parallel, when L and S are anti-parallel. So you see that it is not necessary that only these orientations are possible, because you see that in the previous figure over here we have seen that L and S in this configuration are neither parallel to each other, no, they are anti-parallel. So there is a small energy difference in the two orientations when L and S are parallel and when L and S are anti-parallel. To calculate this energy difference, let us choose the simple Bohr model as the starting point. So you see that in the next few paragraphs, I am going to talk about a magnetic field, which I am going to represent as BL. This is not the external magnetic field, but this is the magnetic field due to the motion of the electron, and is produced internally, not externally. So remember that BL is the magnetic field produced internally by the motion of the electrons. So this is what we are going to discuss. The motion of the electron around the nucleus generates a magnetic field BL at the site of the electron. BL interacts with the mu s, which is the spin magnetic moment. Let's determine the magnitude of BL. You know that BL, why mu s? You know that mu s is a quantity which is a spin related quantity, and the spin angular momentum s, is oriented perpendicular to the axis of rotation of the electron, and it is centered at the electron pointed outward. And similarly, mu s has a direction opposite to that of s vector. So again, mu s is pointed opposite in direction to the vector s, but it is located at the location of the electron. And you know that BL is just, I mentioned that it is due to the motion of the electron, and it is also centered at the electron. So BL and mu s both are located at the same position in the electron, and there will be an interaction between these two quantities. So let us determine the magnitude of BL. Let us consider electron as stationary, while the nucleus is revolving around it as permitted by the theory of relativity. So using the theory of relativity, we can assume that the electron is at rest, whereas the electron is revolving around the nucleus. And this is what we are going to do because we want to make the calculation a bit easier. So let me show you first of all this figure. In this figure, the green spot represents the nucleus with the charge plus E, and the electron is represented by the red spot represented by the charge minus E. V is the velocity of the electron. R is actually the vectorial separation of the electron from the nucleus. You can see the vector L at the location of the nucleus. This is the orbital angular momentum of the electron due to the motion of the electron about the nucleus in a current loop. And you see that this is S. Sz. Sz is actually the Z component of the vector S, and the S, you see that if there is no magnetic field, for example, then you can only represent it by S vector. There is no need to specify Z. But if you are applying, so you see that I have not shown the magnetic field, so only it is only necessary that you just specify the value of S only. But if there is a magnetic field, you can specify the value of Sz. Why we have specified Sz over here? It is because there is an internal magnetic field produced at the location of the electron. And that is what we have mentioned over here in the previous paragraph, that there is an internal magnetic field BL. And due to this internal magnetic field, I am talking about the Z component of the spin angular momentum. Because the later you will see that what is the direction of the magnetic field BL. So here you see that I have shown the geometry in which the electron revolves around the nucleus, whereas the nucleus is located at the center of the current loop. So in the figure shown on the left, the nucleus is at rest and the electron is revolving around it. Now I am going to apply the relativity to the case of electron, assuming that the electron is at rest. In the second figure, you will see that the red spot is shown in the center of the current loop, in the center of the loop, where the electron is located, and we are assuming that the electron is now at rest, whereas the nucleus shown in green is revolving with the same velocity v about the electron with a charge plus e. And you know that in that case, the direction of the orbital angular momentum is reversed, because the separation of the electron with respect to the nucleus is now represented by the vector minus r. And again, v is the velocity of the nucleus. And again, this is the Z component of the spin angular momentum due to the presence of the internal magnetic field, which I have not shown in this diagram. So in the figure shown on the right hand side, the electron is at rest and the nucleus is revolving around it. In the above transformation, R is replaced by minus R, and L is equal to R cross P will be anti-parallel under this transformation, because due to the replacement of R by minus R, the direction of L will be rotated by 180 degree. So L cross R, L is equal to R cross P will be anti-parallel under this transformation. The magnetic field due to the moving charge plus Ze can be found from the Biot-Savart law. So you see that this is what we have assumed, that electron is at rest and the nucleus is revolving. That is, a positive charge is revolving around the nucleus. This is because we wanted to apply the Biot-Savart law. So under that condition, applying the Biot-Savart law to the geometry shown, we have BL, which is the magnetic field at the location of the electron, which is equal to mu naught over 2 pi into Ze over r square. And in the parentheses, we have V cross minus R hat, where minus R hat is a unit vector. So we can replace vector R hat with the vectorial form. So R hat will be replaced by vector over its magnitude. So the magnitude will be multiplied in the denominator, and this is a V cross R divided by R cube. So R square will be replaced by R cube. And then you see that I have taken the negative sign outside the parentheses. This V cross R can now be shown as V cross P, and by dividing it V naught, by dividing it M naught, where M naught is the mass of the electron. And then of course you can see the full relationship shown in equation number 52. That is BL. That is the magnitude of the magnetic field at the site of the electron due to the motion of the nucleus around the electron is equal to mu naught over 4 pi into Ze over M naught into R cube into L vector. So BL, you know, that is directly linked with the angular momentum, with the orbital angular momentum of the electron. So simply here we can say in equation number 53 by writing an inequality that BL is directly proportional to the orbital angular momentum of the electron. And you know that BL has the same direction as that of L. So BL is generated due to the relative motion of the nucleus and the electron. Back transformation. In the center of mass, nucleus is considered at rest, which we usually do, and the electron orbits around the nucleus. Thomas correction of 1/2 can be incorporated and justifiable if complete relativistic calculations are performed. I shall not present the complicated back transformation here. So you see that I am not going to. I have carried out the calculation in the uh, in the in the frame of reference where the nucleus was revolving around the electron, and it requires back transformation where the nucleus will be at rest and the electron will be revolving around that one. And I am not going to calculate that complicated transformation. But you see that if we carry out the complete transformation under the relativistic under the if complete relativistic calculations are performed, then of course we shall notice that a Thomas correction of a factor of 1/2 can be incorporated, which we shall see later on in the calculations that we are going to incorporate. That we are going to incorporate the Thomas correction factor of 1/2. This will be shown later on. So we are not performing the back transformation. Now you see that I am going to show you this picture in which I am showing you that the orbital angular momentum. I have shown you the direction of the orbital angular momentum. I have shown you the direction of the BL, where BL, you know, that has the same direction as that of the angular momentum L, which I have proved in the previous formula. So BL is parallel to L, and you know that this vector S is carrying out a precessional motion about the direction of BL. The direction of BL may be regarded as the direction as the Z direction. So you see that BL is not the external magnetic field, but it is the magnetic field due to the motion of the electron around the nucleus, and it has its location at the site of the electron. So you see that B and L are parallel to each other. So I can show its direction at the location of the electron. You know that the vectors can be displaced anywhere provided their directions and their magnitudes are not changed. So this is vector BL at the location of the electron, and there you can see that the spin angular momentum S will carry out a precessional motion with its tip about the magnetic field BL, shown in a loop, in a green loop. And then, of course, S will have three components: Sx, Sy, and Sz. So Sx and Xy components will be averaged out of zero, and only one component will survive, which is the Sz component, which is the projection of the angular momentum S onto the Z direction or onto the Z axis. So V is the velocity of the electron has also been shown, and here I have also shown mu S. Mu S is the spin magnetic moment, which has a direction opposite to the direction of S. And then you see that when S will precess, mu S will also precess, but about the negative BL direction. And then its projection about the negative BL direction will be represented by mu S comma Z. So this is the picture that I have shown over here. That there is an internal magnetic field BL. And I have shown that if BL is present, of course, it is intrinsic and it will always be present. And you see that S will then carry out a precessional motion about the BL direction. So Bl is produced as a result of the orbital motion of the electron around the nucleus. S and mu s both precess about Bl, one along the positive direction, other along the negative Bl direction. Sz and mu sz are the components of the projections of S and mu s along the z axis or along the Bl axis. The internal energy between the interaction energy between mu s and Bl is given by, so magnetic potential energy between L and S, which is we call VLS, which is due to the spin and orbit coupling, is equal to mu s dot Bl. So this is what we have calculated the magnetic potential energy due to the presence of the magnetic field Bl in interaction with the spin magnetic moment of the electron. So minus mu s dot Bl. And you know that mu s has a value which is equal to minus times gs times e over 2 m naught into vector s. So the negative sign has been cancelled out, and there is a dot product with the value of Bl, and this is what I have shown the value of Bl. So I have taken all the scalar quantities on the left hand side, which is mu naught over 4 pi into ze square over m naught square into r cube, and the vector quantity on the right hand side, which is s dot l. You can also write it s dot l or l dot s, because this is a scalar quantity, scalar vector product. In the above expression, gs is equal to 2. So you see that I have used the value of gs is equal to in this expression. Mu s was substituted using equation number 12.30, and Bl was substituted using equation 12.52. After incorporating the Thomas correction factor of 1/2, the result is, so you see that I am going to include the Thomas correction factor of 1/2 in the previous equation to write the actual relationship, which is shown in equation number 54. So VLS, that is the magnetic potential energy due to the interaction of the orbital quantities with the spin quantities, that is due to the interaction of the spin magnetic moment, spin magnetic moment with the magnetic field due to the motion of the electron, which we call as Bl. So due to the interaction of these two quantities, we have the relationship of VLS shown in equation number 54 after incorporating the Thomas correction factor of 1/2. So you can see that this differs from the previous by a factor of 1/2. So mu naught over 8 pi into z square over m naught square into r cube, and then we have L dot s. So you can write this one as L dot s or s dot L. For z is equal to 1, that is for the hydrogen case, z is equal to 1. The radius is 1 angstrom. Mu naught is equal to 4 pi into 10 to the power minus 7 volt second per ampere meter. M naught is equal to 9.1093837 into 10 to the power minus 31 kilogram is the mass of the electron. And if you substitute these quantities, you will find that VLS has a value equal to 10 to the power minus 4 electron volt. Using this data in equation number 52, will give you the value of a Bl of the order of 1 Tesla, which is equal to 10 to the power 4 Gauss. So you see that this magnetic field produced in a hydrogen atom in its first orbit, when the electron revolves around the nucleus in its first orbit, then the magnetic field which is produced at the location of the electron is of the order of 1 Tesla, or is equal to 10 to the power 4 Gauss. This is the magnitude of the magnetic field. And then you see that I am now going to write equation number 54 in its more precise form or more desirable form. So VLS can be written as A over H bar square into L dot S is equal to H over H bar, A over H bar square into the mod of L into the mod of S into the mod into cos of angle between L and S. So cos of L dot S. This A, which I have introduced in equation number 55, has a value given in equation number 56. That is A is equal to mu naught over 8 pi into Z E square into H bar square over M naught square R cube. This is the value of A. Or this A will later on we shall see is called a spin orbit constant. Spin orbit constant. Because all these quantities are constant over here. So A will be referred to as the spin orbit constant. Now you see that we are going to apply the cosine's law because we want to evaluate the value of cos of L dot S. We want to find out the value of this trigonometric function cos of L dot S. For that one we are going to use law of cosines, which is shown in this figure. You see that this blue arrow represents the value of the orbital angular momentum L, and this black arrow represents the value of the spin angular momentum S, and this J, which is the resultant value of the value L and S, is actually the resultant angular momentum of the electron, represented with the red arrow, and their magnitudes. I have shown only the magnitudes of these quantities. So you see that the magnitude of the orbital angular momentum is equal to the square root of L into L plus 1 multiplied by h bar, where L is the orbital quantum number. And similarly, I have shown the magnitude of the spin angular momentum S mod, which is equal to the square root of S into S plus 1. Outside that one, we have H bar, where a small s on the right hand side is the spin quantum number. And similarly, the magnitude of the vector shown in the red is represented by J mod is equal to J into J plus is equal to square root of J into J plus 1. Outside that one, we have H bar. And this small j in the square root is actually the total quantum number of the atom. So we have three quantum numbers over here. L as the orbital quantum number, S as the spin quantum number, and J as the total quantum number of the atom. And you know that for the case of single electron, the value of S is fixed, which is S is equal to half. So vector addition of the angular momentum vectors S and L to produce the total angular momentum J. And I have in this diagram, I have shown the vectorial form, but I have not shown the vectors thus, and instead I have shown only the magnitude of those vectors. And you know that I am going to apply the law of cosines to this figure as shown in equation number 57. So the cos of L dot S, which I have shown the angle over here, is equal to the magnitude of the square of J mod minus L mod square minus S mod square divided by 2 into L mod into S mod. So you see that you can simply write this quantity as, that is substituting the value of cos of L dot S in the previous equation, that is in equation number 55. If you substitute the value of cos of L dot S that I have calculated in equation number 12.57, you will obtain this relationship, that is the VLS is equal to A over 2 H bar square, and within the parentheses you have J bar square minus L bar minus L square minus L mod square minus S mod square. And if you substitute the magnitude of these quantities, the magnitudes which I have shown in this figure, so replacing these by their actual values in terms of the quantum numbers, you have J into J plus 1 minus L into L plus 1, and S mod square is replaced by S into S plus 1, and I have taken H bar square outside this one, which was cancelled out by the H bar square present in the denominator of equation number 58. So this is VLS, that is the energy due to the interaction of the spin orbit interaction. So you see that this VLS is the spin orbit interaction energy, which is equal to the A by 2. And within the curly bracket, we have J into J plus 1 minus L into L plus 1 minus S into F plus 1. So we have given this energy in terms of the quantum numbers, in terms of the total quantum number of the atom, in terms of the orbital quantum number of the atoms, and in terms of the spin quantum number of the atom. So what is A? A is actually the spin orbit coupling constant. It can be measured from the doublet structure. That is spectroscopically, we can measure this quantity. So it can be measured from the doublet structure in an optical spectra. For any electron, that is for the S, P, D, and so on, for these electrons, the value of S is equal to half, which is a fixed value for the case of single electron, and J will have two values only. So for any combination of L and S, VLS has two values. For larger J, VLS will also be larger. So you see that for the case of single valence electrons, either S electron, either P electron, either D electron, and so on, VLS will have only two values there, because J will have two values, VLS will have two values only, because S and L for the single electron will be fixed. S is always half. For S electron, L will be equal to 0. For P electron, L is equal to 1. For D electron, L is equal to 2. So if you choose an electron, S will be fixed, L will be fixed, J is calculated as we have discussed earlier, that how to calculate the value of the J quantum number. Then you see that put the value of J over there, and then of course for the case of these single electrons, the value of J will be 2. So it means that there are two possible values of VLS. And VLS is actually the spin orbit coupling energy, or the energy that gives you the fine structure energy. So you see that A depends upon the value of 1 over R cube. In this expression, you can see that the value of A so let me show you the constant over here, VA constant. For example, in equation number 56, you can see that the value of A depends on 1 over R cube. So A depends upon 1 over R cube. The quantum mechanical description, in the quantum mechanical description of the atom, there are no fixed orbits. So 1 over R cube is replaced by the theoretical average. So the average value of 1 over R cube is equal to, given by the integral of mod square psi mod square divided by R cube integrated with respect to volume element dV. This is the mechanical quantum mechanical description of calculating the average value of 1 over R cube. What is psi? Psi is the wave function of the electron. dV is the volume element. Let us use Rn is equal to the nth Bohr orbit, nth Bohr radius, as a rough approximation of R. And you know that the nth Bohr radius, as we have calculated in equation number 3.4, that is in slide number 3, equation number 4, the value of Rn was found to be equal to 4 pi epsilon naught into n square, h bar square over m naught ze square. So if you choose this value of R in the expression of equation, in the equation number 56, you will notice that A has a dependence of the type that A is proportional to the value of Z to the power 4 and to the principal quantum number inversely to n to the power 6. So this is actually dependence of this constant A, which we call as the spin orbit constant. So it means that for higher atoms, if for higher atoms the value of Z will increase, so this value A will increase. But if you go for any given atom, if you go for higher values of n, then of course the splitting will decrease. So the splitting will increase if you go along with the higher value of Z, that is for heavier atoms, the splitting will increase, that is A will increase. But for a given atom, if you go for higher values of a principal quantum number, then of course the splitting will decrease. So in equation number 60, so if equation number 60, which I am going to show you this one, I am not going to compute this equation number 60 because this will be more rigorous mathematical calculations are required for the computation of equation number 60. I am skipping that one, but I am just writing down the final result of the value of A. So if equation number 60 is used in equation number 56 after its evaluation, then for a hydrogen-like atom, the following expression is obtained. So A will be approximately equal to Z to the power 4 divided by N to the power cube into L plus 1, L plus 0, then L plus half, then L plus 1. So these three factors will appear in the denominator. So this is what I have given without any mathematical proof. Now I am going to summarize. Summary: fine structure of one electron states. So you see that so far in the last two lectures we have been discussing only the case of one electron state. So again in this lecture I am also discussing the one electron state of the one electron states. That is, only one valence electron is present. Interaction of S and L with L, or equivalently the interaction of mu S with mu L, splits each level into two. That is the doublet case. The result is a doublet level. For example, upper state of the sodium D lines, the 3p state is split into 3p 3 half and 3p 1 half states. These three on the left hand side with both spectroscopic symbols is the principal quantum number. So this 3 is the principal quantum number, and 3 half and 1 half are the total values of values of J, that is the values of the total quantum number J of the atoms. So this is what I am going to show you. This is P. So this is the 3p state. Either you can write 3p over here, or you can simply write p without skipping the principal quantum number 3. So either you can write it in small p or in a large P or in capital P, because we can use both equivalently because it is a case of a single electron. But remember that if you have a case of an electron involving more than one electron, then of course capital P is essential to be written. That is, the capital notation will be written if more than one electron is involved. So this could be either small p or capital P. And this is what I am meaning that I am talking about this 3p electron. This 3p electron, the energy of this electron will be split into 3p half, because with this 3p electron I shall obtain two values of J quantum number, which is equal to 3 half and 1 half. So I have this is you know that this is splitted above the central axis by energy of A by 2, and P half will be shifted downward with an energy equal to minus A. So the magnitude of splitting is given in equation number 59 for the case of single electron. So P to P is equivalently written. And you know that this 3 half and 1 half are the values of total quantum number J of the atom. And for this p electron, you have the value of L is equal to 1 and S is equal to half. So combining them together, you can find out the value of J. For the case of S electron, L is equal to 0, BL is equal to 0, VLS is equal to 0. That is, there is no splitting. Higher value of J, the higher the value of J is, higher is the energy of the state. So you can see over here that the state with value 3/2 is higher in energy than the state with value 1/2. The fine structure splitting VLS is proportional to the value of Z to the power 4. So for heavier atoms, the V splitting will be larger. Fine structure is difficult to observe for hydrogen atom because for hydrogen atom, the value of Z is equal to 1, which is the least value. So the splitting will be very least. So the splitting will be least. That is, the VLS will be very, very small. In principle, VLS is equal to maybe 0 over there, which you can confirm by putting the value of L is equal to 0, BL is equal to 0, VLS will be equal to 0 for the S electron. So for all S electron, and the hydrogen has only one S electron in its ground state, under that condition, the VLS will be equal to 0. So fine structure is difficult to observe in a hydrogen atom in its ground state. Consider 3 lines of the Balmer series: H alpha line, H beta line, and H gamma line. So let's discuss these 3 lines of the Balmer series. H alpha has a value 6562.79 angstrom. H beta has a value 4861.33 angstrom. H gamma line has a value 4340.46 angstrom. The splitting is, so for H alpha, the splitting will be, splitting mean I am going to give you the value of VLS. So VLS value for H alpha line is 0.14 angstrom, 0.08 angstrom for H beta line, and 0.07 angstrom for the H gamma line. So you see that as you go for higher value of the principal quantum number n, you will see that the value of the splitting dramatically decrease drastically, because we are moving for higher values of principal quantum number from H alpha to H gamma line. Splitting of the optical spectral lines into 2 very close components is not possible by conventional spectroscopy. Splitting of optical spectral lines into 2 very close components is not possible by conventional spectroscopy. Why? Because the Doppler broadening of the lines will occur. You know that due to the presence of the Doppler broadening, the 2 very closely lined will merge together, and over a conventional spectroscopic system will not be able to resolve such lines. Though there will be 2 lines there, doublet lines, but you know that those doublet lines for the case of single electron, even with conventional microscopy, cannot be observed, and you will be able to observe only a single line due to the presence of the Doppler broadening. Now consider a line of the first primary series of the cesium atom. Lambda is equal to 8943 angstrom. Lambda 2 is equal to 8521 angstrom. The delta lambda between these 2 lambda, the difference of wavelengths, is equal to 422 angstrom. And in terms of the wave number, it is a 544 centimeter inverse. So you see that this is a very large splitting between a lambda 1 and a lambda 2. Because the cesium atom is a heavier atom. For that one, the splitting is very large. So splitting is so large that the 2 lines are difficult to recognize as component of a pair. So in the spectrum, it becomes difficult to recognize that lambda 1 is associated with lambda 2, or lambda 1 is a doublet partner of lambda 1, because lambda 2 is splitted so much away in the spectroscopic findings that we cannot, if we do not understand the theory correctly, we shall separate lambda 2 as not as a doublet part, but as some other wavelength, individual wavelengths. So you see that in this case, lambda 1 and lambda 2 are very well separated from each other. That is, the doublet has a very large splitting with each other, with respect to each other. So the splitting is so large that the 2 lines are difficult to recognize as component of a pair. For sodium, D lines D1 and D2 are separated by delta lambda is equal to 6 angstrom, which is equal to 17.2 centimeter inverse, and the splitting is easily observable even with conventional spectroscopic apparatus. So splitting is greatest for smallest n, because n, you know that n cube is occurring in the denominator. So if n is small, the splitting will be large, and you can have a reasonable value of the constant a. And then of course, as in case of d1 and d2 lines, you can see so you can see those splittings as the doublet lines. So symbol for energy terms. So you see that in the spectroscopic energy terms, I am now summarizing that the spectroscopic energy term will be written as n, written on the left hand side, is the principal quantum number. The symbol, the spectroscopic symbol, the spectroscopic notation, this is the notation, spectroscopic notation. And the S, capital S, is actually the spectroscopic symbol. Could stands for capital S, capital P, capital T, capital F, and so on. So this S, capital S, has the positions of capital S, capital P, capital T, capital F, and so on, depending upon the value of the orbital angular momentum quantum number. So if L is equal to 0, we choose capital S. If L is equal to 1, we choose capital P. If L is equal to 2, we choose capital T. If L is equal to 3, we choose capital F, and so on. And you know that here is M. M is actually the multiplicity. Multiplicity capital M is equal to 2s plus 1. For this case of single electron, this capital S will be represented as small s. And you know that the small s has a fixed value. For the case of a single electron, the value of the small s is equal to 1/2. So if you put the value of 1/2 over there, you will find that the multiplicity will be equal to 2. So multiplicity will give you the possible values of the total angular momentum quantum number J. So if the value of M is 2, then J will have 2 values. So if M is equal to 5, then J will have 5 values. So M is equal to 2 for the case of a doublet, that is for the case of single electron, except that L is equal to 0. Because when L is equal to 0, the multiplicity will still be equal to 2, but only a single line will appear, as I have explained earlier. So M is the multiplicity given by capital M is equal to 2s plus 1. So capital S is the case when we have more than one electron is present, which this case will be discussed later on in some lecture in the future. But for the case of single electron, this capital S will be represented by small s, which has a fixed value equal to half. And this J is actually the total angular momentum quantum number. So you see that in the spectroscopy analysis, we have this notation in which we have principal quantum number and the total quantum number, and the orbital quantum number is represented in terms of these notations, and then we have the multiplicity. For single electron systems, the terms are doublet terms. That is, the two will be split into two terms, because the spin of the electron can have two orientations with respect to the orbital angular momentum. Capital S terms are not split, but still we write the multiplicity equal to 2. For a valence electron with n is equal to 2, L is equal to 0, S is equal to half, J is equal to 1/2. Because J is calculated using L and S, which is equal to 1/2 only a single value. So the term will be equal to 2. This 2 is due to is due to principal quantum number, and this 2 as a pre-superscript is the multiplicity, then S is the symbol corresponding to L is equal to 0, and this half is the value of J. So for N is equal to 2, L is equal to 1, S is equal to half, J is equal to 3/2 and 1/2 are the two values of J, which result by the combination of L and L plus minus S mod. and then you see that the terms will be 2p 1/2 and 3/2. Two energy terms could be seen. It means that we have the case of doublet because we have two values of J. Now alkali scheme of now level scheme of the alkali atoms. You see that we have discussed the alkali atoms earlier. So I have discussed the alkali metal atoms in one of the previous lectures, and now I am going to refine my discussions as far as the alkali scheme or alkali atom scheme are discussed. So in this diagram, you can see that there are horizontal dotted lines shown in the black. These corresponds to the levels, principal levels corresponding to the principal quantum numbers of the hydrogen atom. So you see that corresponding to n is equal to 2, you can see a horizontal dotted lines in black. Similarly, corresponding to n is equal to 3, and similarly corresponding to n is equal to 4, you can see the horizontal dotted lines corresponding to the energy of the hydrogen atom corresponding to these principal quantum numbers. So I have shown over here S, P, D, and F. So these are the 4 electrons that I am showing their energies for the alkali metal atoms. For the s electrons represented by capital S, for which the orbital angular momentum is equal to 0. And you see that I am showing over here, this half is actually the value of the total angular momentum quantum number. So half, then again half for the n is equal to 2 case, and for the n is equal to 3 case, you can see that the value of the that is the value of the total angular momentum J of the atom is 1/2 in all these cases. So there is a single line. This is a singlet case. So for the s electron, there is no splitting, you can see. For the alkali metal atoms, only one level is present. And you can notice their locations with respect to the energy of the hydrogen atom. That's with respect to the locations of the principal quantum numbers of the related with the hydrogen atom. So you see that the first value is lying there. You see that I am going to present this data for the case of 2s electron, 2p electron, 2d electron, 2f electrons. So for the 2s electron, you can see that its energy, which is 1/2, is much below the principal energy level n is equal to 2. And you can also notice that the level 1/2 corresponding to the principal quantum number 3 is also much below the reference line. Similarly, you can see that the energy level corresponding to 1/2 and with level 3s level is also much below the principal quantum number 4. So what we can notice is that so you see that this first line is due to 2s electron. This line is equal to 3s electron. This line is due to this is due to 2s electron. This is equal to 3s electron. And you know that in alkali metal atoms, the energies lies much below the reference energies for the hydrogen atom. Now let's move to the p electron. The first two levels that I have shown at the lowest p is actually the 2p electron. You know that for the 2p electron, the value of orbital for the p electron, the value of the orbital angular momentum L is equal to 1. And you know that S is always half for the case of single electron. So there are two values of J. So these two are the splittings due to the 2p electron with the principal quantum number J equal to 3/2 and the principal quantum number J is equal to 1/2. So with 2p, so this was equal to 2p, and the next one is equal to 3p. This is due to 3p. You can notice that their energies are below the hydrogen reference line, but their energies are above the s levels of the s electron. So again, you can see that 3½ is above in energy than the 1½ level. And at the topmost, which corresponds to the 3p electron. So this is the energy. These are the two doublet levels corresponding to the 3p electrons with the energies 3½ and with the energies 1². So with p, you have the doublet lines. You can see doublet lines. So for each, for 2p, for 3p, for 2p, for 3p, for 4p, you would notice that there will be doublet lines. And each doublet line has two values of allowed quantum number j's, 3/2 and 1/2, 3½ and 1/2. Here you will notice that one thing to notice is that their energies lie below the reference energies of the hydrogen atom, but their energies lie above the energies of the three of the s electrons of the corresponding s electrons. But you can also notice that the energy difference between between these states, between these doublet states, will decrease as you move with greater number of principal quantum numbers. So the energy separation between them will decrease with the increase in principal quantum number. So now let's move to the d electron. For the d electron, the value of the orbital quantum number is 2, and the value of the spin is ½ So again, you see that you have the doublets with the values of quantum number j is equal to 5½ and 3½ And again, you can see this is the case of 3½ 3, that is the principal quantum number is 3 over here. And then you see that there are doublet lines 5½ and 3½ which lie below the line of the hydrogen reference line with the principal quantum number 3. And these two lines lie above the energies, lie above in energies with respect to the p electrons, with the corresponding p electrons. And the next one is the 4d electron, again with the two doublets with the 5½ and 3½ splittings. And you see that as you move again with the higher principal quantum number, you can see that the energy gap between them will decrease. So the red lines will narrow down with the increase in principal quantum number. And you see that I have shown only one line for the F, for the 4f electron with the values of total angular momentum j equal to 7½ and 5½ Again, this is the case of a doublet line. For the case of the 4f electron, again the value of the 4f electron, you see that it is now much closer to the hydrogen, to the level of the hydrogen level corresponding to n is equal to 4. So as we move with the higher values of the electron with the orbital with greater value of orbital quantum numbers, you can see that their values approaches to that to the values of the hydrogen atom. That is the difference between them, between their levels, and that of the levels of the hydrogen atom will decrease. And if you move from bottom to top with the increase in principal quantum number, you will see that the splitting will decrease. You see that I have shown only 3 sets of transitions between these levels, which were allowed by the optical transitions. Delta J is equal to 0 plus minus 1, and delta L is equal to plus minus 1. So you see that delta is equal to delta L is equal to plus minus 1 means that S can make a transition to P can make transitions to D. Similarly, P can make transitions to S, and P can make transitions to D. But S cannot make transitions to D. Similarly, P cannot make transitions to F because delta L is equal to plus minus 1 will be violated. Similarly, the values of capital J, the values of the J quantum number can make transitions. For example, in this case from 3½ to 5½ And similarly 3 half to 3 half is also possible, but from 1 half to 1 3 half is possible, but from 1 half to 5 half is not possible, because that is not permitted by j is equal to 0 plus minus 1. So you see that under these two selection rules or the optical selection rules, the level schemes of the alkali metals are explained with the presence of the doublet lines for all the p, d and f electrons except for the s electrons, which has the singlet lines. And for all the others, the angular momentum j, the total angular momentum j of the electron has two possible values, that is a multiplicity is 2, and these lines are called the doublet lines. And the three set of transitions have been shown to explain the selection rules, optical selection rules given by delta J and delta L. So the greater the value of J, the greater the value of the energy term. States corresponding to one valence electron of alkali metal atoms. States corresponding to one valence electron of the alkali metal atoms with spin orbit coupling, that is LS coupling. That is the interaction of the orbital magnetic moment with the spin magnetic moment, or more precisely the interaction of the magnetic field Bl with the spin magnetic moment of the atom. The terms are displaced with respect to those of the hydrogen atom indicated by the dotted horizontal lines. The S terms are displaced the most. The S lines are displaced the most. The fine structure splitting decreases with the increase in values of N and L. Some transitions and the selection rules are given. So you see that the value of L will increase as you move towards the right side. That is, you move from S to P, from P to D, from D to F. The splitting narrows down with the increase in value of L. And if you move from for higher values of N from bottom to top, you will see that the splitting will decrease. Optically allowed transitions follow the selection rule. Delta L is equal to plus minus 1 and delta J is equal to 0 plus minus 1. Optical transitions are allowed only if the orbital angular momentum changes. So you see that this is an important point over here. Optical transitions are allowed only. This is the physical thing that I am going to explain. That is, the optical transitions are allowed only if the orbital angular momentum changes. J, however, can remain the same if L and S change in opposite directions. J can remain the same provided L and S change in opposite directions. Let me explain this one. By considering the transition from 2d3 half to 2p3 half. From 2d3 half to 2p3 half. So you see that I am considering only one transition from this 2d3 half to 2p3 half, this line. So let me explain this line. So let's consider the transition from 2d3 half to 2p3 half. You know that for the d electron we have L is equal to 2, and since there is only one electron involved, the value of S is always equal to half. So you see that if you want to produce 3 by 2 as the total angular momentum J of the atom, you need to compute this L minus S mod. So if you put the value of L and S over here, you will get 3 by 2 as the value of J. So here from the sign of the L and S quantum numbers, you can notice that L and S are anti-parallel. Now let's consider the 2p3 half state. When with P you mean that L is equal to, from the value of capital P you mean that L is equal to 1. Since only one electron is involved, S is equal to always half. Now you see that in order to produce 3 half using the value of L is equal to 1 and S is equal to half, you need to add them. So L plus S will give you a value of equal to 3 half, which means that from the sign of the plus sign, you can see that L and S are parallel to each other. So for the D transition from the 2D3 half to the 2P3 half, you will notice that the transition from the, that is for the J, for the same value of J, for the same, however, for the same value of J can remain the same if L and S change in opposite directions, which is demonstrated over here. That is for the D, L and S are anti-parallel to the transition to the case when L and S are parallel, provided they have the same J values. So if the values are, if the values of J are the same and the transition has occurred, it means that under this transition, the L and S has moved from parallel combination to the L to the anti-parallel combination and vice versa. Now I am going to discuss some series briefly, which I have already discussed in one of the previous lectures, especially on the lectures on alkali metal atoms. So series in the alkali metal atom, the principal series with the principal quantum number n shown 2s half to the transition with n greater than equal to the principal quantum number n, and with the 2p half and 3 half, with the 2p 1 half and 3 half. This arrow, this double-sided arrow shows that the transition is a resonant transition. That is, the transition from P to S and from S to P are equally possible. And you know that for this principal series, we have seen earlier in the alkali metal atom lectures that n should be greater than equal to the principal quantum number with P should be greater than equal to n. So where n is equal to 2, 3, 4, 5, 6, and so on for the lithium, for the sodium, for the potassium, for the rubidium, and for the cesium respectively. So if you want to talk about the principal series for these atoms, you need to plug in the appropriate value of the principal quantum number n, so that you can obtain the principal series from these respective atoms of the alkali metals. So one observes a pair of lines from this. That is, the doublet lines will also be observed under these transitions, because we have the p values, which is the 2, 1 half and 3 half. So these are the doublet lines. Now let's consider secondary series. Secondary series. Again, you see that we have the principal quantum number n, and we have 2p 1 half, 3 half, and the transition is towards S1 half. And for this series, the principal quantum number with the S1 half should be greater than equal to n plus 1. This series is also what we have discussed in the lecture on alkali metal atoms. So for this series, n must be equal to 2, 3, 4, 5, 6 for lithium, sodium, potassium, rubidium, cesium respectively. And one observes a pair of lines also, because again you see that P is a doublet with two energy levels, 1 half and 3 half. Then we are moving towards the diffuse or the first secondary series, from the 2p 1 half, 3 half to 2d 3 half and 5 half. And you know that there is a condition on the principal quantum number. So if you write the principal quantum number n with the 2p 1 half, 3 half, then the principal quantum number with 2d 3 half, 5 half should be greater than equal to n. And again, this is a resonant transition with arrow indicated with the double arrow. So let me show you the transition between two levels. You know that 2d 5 half and 2d 3 half greater in energy are shown, and the other two lower energies, lower energy levels are shown with the 2p3 half and 2p1 half. Three possible transitions under delta J is equal to 0 plus minus 1 are shown. Two transitions for the level p3 half and one transition for the level p1 half, because the transition for the level from d5 half to p1 half is not allowed. So these are the triplets. So you know that this is the case of triplet transition. So these are the triplet, that is three transition lines. Now revisit figure on page number 10 and page number 10 of slide number 11 and make corrections according to delta J selection rule. Because there I didn't mention the delta J selection rule, and I didn't follow the follow the delta J selection rule there perfectly. But now you can, I have demonstrated the delta J rule very clearly, and if you can also, if you want, you can refine the figure on page number 10 of slide number 11 using the delta J rule. In the said figure, only delta L selection rule was applied. So now both delta L and delta J selection rules must be applied and must be obeyed as far as the optical transitions are allowed. So you see that this lecture is continued up to the next lecture. So this lecture is not finished yet, but it is continued. So as far as this lecture is concerned, this is the end of this lecture. So this is the end of slide number 12C of the course on atomic and molecular physics. But this lecture is continued to the next one.